Okay, I guess probably close enough time, so we'll go ahead and start. This is the direct instruction for 3/21/2016. Now these topics will be a little bit different than past direct instructions. Some of these have a step-by-step, and some of them just you have to see the property and then you apply it in whatever circumstance. So it's maybe not as clear-cut. Now this first one says domain of a rational function. Now rational function is a function with a single fraction. Now specifically, we're going to have variables involved. And typically the variables are in the denominator, but they don't have to be. But again, rational means single fraction. To find the domain of a rational function, first thing you do is you set the denominator equal to 0, and then you solve. And then step 3 is you put a slash through the equals. And I'll show you two different ways of writing your domain, so you see, just in case the quiz has it in both one way or the other way. Now I pulled these out of the textbook. Hopefully I wrote these down correctly. This is page 378, number 15. We got h of x is equal to 4 over x minus 3. And the instructions are to find the domain. Domain is all your possible x values. Step 1, set denominator equal to 0. So we'll set the x minus 3 equal to 0. Step 2 is to solve. So in this one, I take negative 3 over, and we get x is equal to positive 3. Now this is the value we cannot have. If I put 3 up in my original function, I'm going to have 3 minus 3 in the denominator, which gives us division by 0. So can't have that. So step 3 says put a slash through the equals. So x cannot equal to 3. Now that's one way you see your answers written. And sometimes I write it in interval notation. Interval notation would go from negative infinity to 3, parentheses on the 3 to not included, union, parentheses on the 3 to not included, and it goes up to positive infinity. So those are the two ways you usually see them in multiple choice form. Let's take a look at 31. I got a of x is equal to 5x plus 2 over x squared plus 2x minus 24. Same instructions. Want to find the domain. Step 1. Set the denominator equal to 0. So we got x squared plus 2x minus 24 equal to 0. Step 2, solve. Well, this one factors using the PST method. And factors as x plus 6 times x minus 4. Now the zero factor property says you get 0 on one side, you factor the other side, you set each factor equal to 0. So I can set x plus 6 equal to 0, and I can set x minus 4 equal to 0. And that gives us x equals negative 6, and x is equal to positive 4. Again, these are the values we cannot have. If I were to put it back up here for x, for example 4 squared is 16, 2 times 4 is 8, 16 plus 8 is 24, 24 minus 24 is 0. So step 3 is we want to put a slash through the equals. X cannot equal negative 6, and x cannot equal to 4. Now in terms of interval notation, you go from negative infinity to your smallest number, which is negative 6, parentheses, union, then your smallest number to your largest number, parentheses around both of them, union, and then your largest number up to positive infinity. And that says the same thing as putting the slashes. Number 27. I'm not sure if I wrote it down right, but let me just say f of x is equal to x plus 1 over x squared plus 1. And same instructions, one find the domain. Well, we're going to, step 1, set our denominator equal to 0. Now to solve this for x, we use a square root property. And we're going to see this a little bit later tonight when we talk about the Pythagorean theorem. Square root property says if you got something squared equal to something else, then you drop your squared and you put a plus or minus square root around the other side. So in this one I need to take the 1 over to the right side, and it becomes a negative 1. Now square root property says we're going to drop our squared and we put a plus or minus square root around the other side. Now this is covered in almost the last section, I think, and we'll talk about this. But this would give you an imaginary number. Whenever you have a plus or minus, or whenever you have a square root of negative 1, that always gives you an I. Now domain is a very practical item. So when we say that's the value we're going to exclude, whenever you have an I pop up, you just drop it away. So then step 3 changes a little bit. Our domain is simply negative infinity to positive infinity. Or you can write all real numbers. Unfortunately, books sometimes introduce topics before they're really covered, and this is one case where they have it. Or you could simply up here say you cannot factor it, which you could say negative infinity, positive infinity. That's not quite true all the time, though. If you use a quadratic formula, there may be some here that give you a couple answers that you want to exclude. But we'll see complex numbers, I believe, in the last section. But that's finding the domain. So we have our case where you have a linear x minus 3. We have a quadratic x squared plus 2x minus 24. And then we're one where you can't factor. And if you tried to solve it using another technique, you'd end up with an imaginary number. Let me clear those off. Now the domain of a radical function. So finding the domain of a radical function. You set what is under the radical greater than or equal to 0, and then you solve. This goes back to what we just talked about. You can't have a negative number underneath a radical. Now I don't have any problems picked out of the book on this, but these I can make up. Let's say we got f of x is equal to the square root of 3x minus 1. And the instructions say to find the domain. Actually, this is domain of radical function with an even index, which is there is no radical with an odd index in the assignment I could see, so it's pretty much square root. Now the index is whatever number is in this little slot right here, and if there is a number here, it's by default 2. So this is a radical with an even index. So step 1, we're going to set what is under the radical, which is 3x minus 1 greater than or equal to 0, and then solve it. So take the negative 1 over, becomes a positive 1. Divide both sides by 3, and you got x is greater than or equal to 1/3. Now that's our domain. If you want to write it in interval notation, it'd be a bracket because it's a greater than or equal to. A line underneath means bracket. And then we go to 1/3 to positive infinity. So either way would represent the same value. Now, even though I said I don't think there is any, let me make up one, just in case there is. Let's say I have an odd number in this slot here. That's your index. Well, these really are two exceptions. If you have a fraction, you handle it this way. If you have a domain of a radical function with an even index, you handle it this way. And if you have a radical with an odd index, like 5, then your answer will simply be negative infinity, positive infinity. And that's our domain of a radical function. Now let's take a look at simplifying rational expressions. Let me clear up this page. So simplifying rational expressions. Step 1, factor the top, factor the bottom. So factor the numerator, factor the denominator. Step 2, cancel if possible. This is off of page 379, number 63. We got x squared minus 7x plus 12 over x squared minus 9x plus 20. And instructions here are to simplify it. Well, step 1, factor the top, factor the bottom. Both of these factor using the PSD. The top part factors as x minus 3 times x minus 4. And the bottom part factors as x minus 4 times x minus 5. Step 2 says cancel if possible. And when I say cancel, if you have the same item on top and on the bottom, then you can cancel them. See how we have an x minus 4 here and x minus 4 here. So those both will cancel. And then I'm left with x minus 3 over x minus 5. Now you might wonder, why can't you cancel the x's? Everything has to be multiplication for you to be able to cancel. Since this is x minus 3, I cannot cancel these x's. Up here, we had this set of parentheses times this set of parentheses, so that was multiplication. And here we had this set of parentheses times this set of parentheses, so that was multiplication. That's why we could cancel the x minus 4's. A lot of people try to cancel the x squareds up here and the x's, and you can't do that, because everything has to be multiplication. Now that's our simplifying rational expressions. And let me cut that, paste it right here. In the book, they cover multiplying, dividing rational expressions first. These list of topics I pulled out of the unit in the course. Not necessarily the best order in covering them. So we'll do multiplying, dividing rational expressions because that actually makes more sense with what is before it. Okay. Multiplying rational expressions. Step 1. Factor everything. Step 2. Cancel if possible. Only guideline is that 1 is on top and 1 is on the bottom, and they're the same. Step 3, multiply the tops, the numerators, and multiply the bottoms, the denominators. Pretty much every time we deal with rational expressions, you have to be good at factoring. That's kind of key on it. So let me clear that off. And this one is on page 387, number 5. We've got 3x minus 15 over 4x squared minus 2x times 20x squared minus 10x over 15x minus 75. Now step 1 says to factor everything. 3x minus 15, that'll be GCF. They both have a 3 in common. 4x squared minus 2x will be GCF. They both have a 2 and an x in common. This will be GCF. They both have a 10 and x in common. And this one will be GCF. I think they're both divisible by 5 or 15. So here I factor out a 3, and that gives me x minus 5. Here I factor out 2x, and that gives me 2x minus 1. Up on top here, I factor out a 10 and an x, and that gives me 2x minus 1. In factoring, if it looks like everything's disappeared, this 10x looks like you took it all out in front, you never left it blank. Because remember, a factor means to divide out. So 10 divided by 10 would leave us a 1. And then on the bottom, both divisible by 15, x minus 5. Now then step 2 says cancel if possible. Only guideline is that one's on top, one's on the bottom, they're the same. Here's an x minus 5, here's an x minus 5. Those are going to cancel. Here's a 2x minus 1, here's a 2x minus 1. So those are going to cancel. So we got 3 over 2x times 10x over 15. Now you cannot forget your rules from before. First off, notice how these both have an x here and x here. One's on top, one's on the bottom, they're the same. So those x's are going to cancel. So then we're left with 3 halves times 10/15. And number-wise, remember if you got a number on top, a number on the bottom, they're both divisible by the same number, then you divide them. Here I got 2 and 10, they're both divisible by 2. 2 divided by 2 is 1, 10 divided by 2 is 5. Now I'm showing a lot more steps than you need to. Okay. Well, here we have 3 and here we have 15. Those are both divisible by 3. 3 divided by 3 is 1. 15 divided by 3 is 5. So we got 1 over 1 times 5 over 5. And here I got 5 and 5. They're both divisible by 5. That gives you 1. That gives you 1. So I got 1 over 1 times 1 over 1. There's nothing else we can cancel. So step 3 says multiply the tops, multiply the bottoms. 1 times 1 is 1. 1 times 1 is 1, and 1 over 1 gives us 1. That seemed to come out really nice. Let me just double check myself here. Okay, x's cancel, 30 over 30, yeah, it's 1. Now let's look at one with a little bit harder factoring. This is number 9. We got x squared minus 3x plus 2 over x squared minus 8x plus 15 times x squared plus x minus 12 over 8 minus 2x minus x squared. Now step 1 says to factor everything. Well, the top of our first fraction is PSD, x squared x, no number in front of x squared. The bottom is PSD, x squared x, no number in front of x squared. This is also PSD. This one is in wrong order. We want the problems to be in standard form. Terms range from largest power down to smallest. Okay, so this one factors as x minus 1 times x minus 2. This one factors as x minus 3 times x minus 5. This one factors as x plus 4 times x minus 3. And to put this in the right order, we'd have a negative x squared minus 2x plus 8. Now, I see that it starts with a negative, so GCF says we're going to factor out a negative. Now I could do some canceling, but I'm going to follow my steps strictly. So all these are going to carry down because I'm not done with step 1 yet. Factor everything. Okay, so I factor out a negative 1, and that gives us x squared plus 2x minus 8. Remember, when you factor out a negative, it flips the sign of everything. And now what's inside the parentheses would be the PSD. So I'm going to have x minus 1, x minus 2, x minus 3, x minus 5, x plus 4, x minus 3, and negative 1 times x plus 4, x minus 2. So now I've factored everything as much as I can factor it. Step 2 says cancel if possible. The only guideline is one's on top, one's on the bottom, are the same. Here's an x plus 4, here's an x plus 4. Here's an x minus 3, here's an x minus 3. You notice they can be in the same fraction, or they can be in different fractions. Again, only guideline is one's on top, one's on the bottom, are the same. Here's an x minus 2, and here's an x minus 2. So that's going to leave us x minus 1 over x minus 5 times, nothing's left up on top. If everything disappears, I think I live next to the train yard. If everything disappears, we're left with a 1 there. So we're left with, on the bottom, negative 1, I guess is it. Okay. Now, there's nothing left to cancel or anything, so step 3, multiply the top parts together, multiply the bottom parts together. X minus 1 times 1 is x minus 1. And this negative, a lot of times they'll put it out in front of the fraction like that. Or if you put it down below, it would look like x minus 1 over negative 1 times x minus 5. which would give you x minus 1. And when you multiply everything by a negative, you get negative x plus 5, like that. Some books will actually write that as 5 minus x. I never did bother to look at the answers on these to see how they write them. But different ways you can write them. And that would be multiplying rational expressions. Now the second part of that is dividing rational expressions. And really there's not many steps for dividing rational expressions. Let me clear this off. Dividing rational expressions. We never actually divide. We rewrite it as multiplication by changing the division symbol to multiplication and flipping the fraction following the division symbol. When I say flipping the fraction, I'm talking about the reciprocal. Then multiply like normal. So again, we never actually divide. We just immediately rewrite as multiplication and then go from there. This is number 25 on page 387. And we got 2x squared minus 5x minus 3 over 2x squared plus 7x plus 3 divided by 2x squared minus 3x minus 20 over 2x squared minus x minus 15. Okay. So this first fraction remains as is. We change the division to multiplication, and we flip the second fraction. Take reciprocal of it. So the bottom goes to top, top goes to bottom. So we're going to have 2x squared minus x minus 15 over 2x squared minus 3x minus 20. And then we're going to multiply like normal. Our first step to multiplying is to factor everything. This would be key number because there's a number in front of the x squared. This would be key number, same reasoning. All these would actually be key number. So this becomes 2x factors as, let me double check that, 2x plus 1 times x minus 3 and the bottom, the first fraction becomes 2x plus 1 times x plus 3 The top of the second fraction becomes 2x plus 5 times x minus 3. And the bottom of the second fraction becomes 2x plus 5 times x minus 4. You can see on these that there's a lot of factoring. This is why you have to feel fairly comfortable with the factoring. in order to do these problems. Now I'm writing down all the techniques I'm using. I'm not showing all the steps for that, but that way you can go back and you can refer to that technique to refresh your memory on how to factor that. Step 2, cancel. Again, your only guideline is they're the same, and one's on top, one's on the bottom. Here's a 2x plus 1, here's a 2x plus 1. Here's a 2x plus 5, here's a 2x plus 5. Now I have an x minus 3 here and x minus 3 here, but both of them are on top, so I can't do anything with that. So I'm left with x minus 3 over x plus 3 times x minus 3 over x minus 4. Step 3 on multiplying is multiply the tops and multiply the bottoms. So we're going to have x minus 3 times x minus 3, and on the bottom would have x plus 3 times x minus 4. Now the top, you might see them write it as x minus 3 squared, and this is x plus 3 times x minus 4. Although every book's different, usually they don't actually multiply this back through. They leave it in this form. And there's a reason for that. If you were to go on and take calculus of some sort, this is a better form to have it in order to do something further with it. Again, as always, though, if you have any questions we're going through this, be sure to ask. Let's take a look at adding and subtracting rational expressions. So adding and subtracting rational expressions. Step 1 is to get a common denominator. Now I'm going to write this in terms of the harder problems. Some of them means you don't have to do these steps. But to get a common denominator, you have to typically factor all your denominators. Figure out the LCD of all the denominators. And we'll talk more about that. And rewrite each fraction with that new denominator. In step 2, we add or subtract the top parts and put into a single fraction. And then step 3 is simplify the fraction. And that's what we saw up above, simplifying a rational expression. So these are going to be our steps we're going to go through. Let me clear off this page. This is off page 390, number 81. Okay. Now our first step is get a common denominator. And the first sub-step within that is factor all the denominators. Now x plus 5 we can't do anything with, but this one is PSD. So we're going to have 2x minus 3 over x plus 5 minus x squared minus 4x minus 19 over x plus 3 times x plus 5. Now B and C kind of go together. It says figure out the LCD of all the denominators. LCD is least common denominator. Now we take a look at each factor. I'll start with the x plus 5. And we're looking for the greatest number of x plus 5s in any single denominator. There's one here, and there's one here. So the greatest number of x plus 5s in any single denominator is 1. Then I go to my next factor, the x plus 3. Now I'm looking for the greatest number of x plus 3s in any single denominator. There's none here, there's one here, so the greatest number of x plus 3s in a single denominator is 1. And now it would be our least common denominator. Now, the third substep on that says to rewrite each fraction with that new denominator. Now our second fraction already had that denominator. It's reversed, but multiplication is commutative, so that's okay. So we don't change it at all. But our first, in our first fraction, we had the x plus 5. The x plus 5 is still there. The new item that we put down below is the x plus 3. Now whatever new item you put down below, you also have to put up on top. The mathematical principle behind that is whatever you multiply by the denominator, you also multiply by the numerator. So then 2x times x is 2x squared. 2x times 3 is 6x. Negative 3 times x is negative 3x. And negative 3 times 3 is negative 9 over our denominator. And this one remains as is. Two x squared, 6x minus 3x minus 9. Okay. Then combine together like terms. 6x minus 3x is 3x. And our denominator stays as is. You notice I'm not multiplying the denominators together. I don't actually want to do that. We'll talk more about why in here in a minute. Okay, so that was step 1. They got the same denominator now. Now step 2 says to add or subtract top parts and put it into a single fraction. So we're going to have 2x squared plus 3x minus 9. Now the minus has a special circumstance that goes with it. This will flip the sign of all the terms up on top of the second fraction. So the x squared becomes a negative x squared, the negative 4x becomes a positive 4x, and the negative 19 becomes a positive 19. And our denominator remains as is. Now if you just got a plus between these, then nothing special, you just put all of them together in one numerator. Combine together like terms. Here's an x squared, and here's an x squared. 2x squared minus x squared is x squared. Here's a 3x, and here's a 4x. That gives us 7x. And here's a negative 9 plus 19, which gives us plus 10. Okay, then step 3. Step 3 said simplify the fraction. And remember, in simplifying these, you factor the top and factor the bottom. The top part will factor with PSD. Bottom part I don't need to worry about because it's already factored. This is why you never want to multiply it back through in the denominator, because it's already in the right form. We got something times something else. and you're hoping at the very end it'll cancel. Well, the top part factors as x plus 2 times x plus 5. Now notice after I factor, the x plus 5 is going to cancel. And that's going to leave us x plus 2 over x plus 3. And that's our answer. Actually, when I picked that one out, I didn't think it'd be that hard. That one is a little bit hard. This next one's a harder one, so let's take a look at it. Let me clear off this page. When we get to the radicals, the nice part about radicals is the problems are a lot shorter. But the worst part of them is there's no step-by-step approach that you can take in these. Okay, let's take a look at this one. Step 1. Get a common denominator. And first sub-step is factor all the denominators. Well, this is PSD, and this one's PSD. So we got x plus 1 over x plus 3 times x minus 2 minus x plus 2 over x plus 1 times x plus 3. Now on B, we want to figure out our common denominator. Well, let's start with our first factor, the x plus 3. Now I'm looking for the greatest number of x plus 3's in a single denominator. There's one of them here, and there's one of them here. So the greatest number of x plus 3's in a single denominator is 1. We're not counting how many there are. We're looking for the greatest number of them in a single denominator. Then I go to x minus 2, and I'm looking for the greatest number of x minus 2's in a single denominator. There's one here, there's none here, so the greatest number of x minus 2's is 1. And then I go to my next factor, the x plus 1. And I'm looking for the greatest number of x plus 1's in a single denominator. There's none here, there's one here, so my greatest number of x plus 1's is 1. So that's going to be our least common denominator. Okay. Now our third substep says to rewrite each of them with that new denominator. So let's see what's happened here. Here's an x plus 3, here's an x plus 3. Here's an x minus 2, here's an x minus 2. They're both still there, which they always will be. The new item down below is the x plus 1. So whatever new item we have down here, we have to put up on top. Again, the mathematical principle is wherever you multiply by the denominator, you have to multiply by the numerator. Now in the second fraction, here's an x plus 1, the x plus 1 is still there. Here's an x plus 3, the x plus 3 is still there. That new item is the x minus 2. So whatever new item we have down below, we have to put up on top. Now multiply these top parts together. X times x is x squared. X times 1 is 1x. 1 times x is 1x. 1 times 1 is 1, all over our denominator. Minus x times x is x squared. X times negative 2 is negative 2x. 2 times x is 2x. And 2 times negative 2 is negative 4, over our denominator. which gives us x squared, combine like terms, 1x plus 1x is 2x, plus 1, over our denominator, minus x squared, negative 2x plus 2x cancels, so that gives us x squared minus 4 up on top. And now they have the same denominator. So step 2. We're going to add or subtract the top parts and put into a single fraction. So we're going to have x squared plus 2x plus 1. Remember, if you have a minus in front of your fraction, this flips the sign of all the terms up on top. So the positive x squared becomes a negative x squared. The negative 4 becomes a positive 4, all over our denominator. Combine together like terms, x squared minus x squared drops away. And I guess there's nothing to combine together with the 2x. So I got 2x. And then I got 1 plus 4, which is 5. Over our denominator. Now normally step 3 would be to simplify, but there's nothing I can cancel. Nothing factors out of the 2x plus 5, assuming no basic math error up above. I didn't actually write down the answers of these. X squared minus 4, x squared plus 2x plus 1, plus 5. Okay, I don't think I missed anything. But that would be our answer. Typically, you do not multiply these back through. You leave it in this form here. Adding and subtracting rational expressions isn't a very pretty process. Let's take a look at complex rational expressions. This is where you got a fraction inside of a fraction. Typically, a complex fraction, definition of it is a fraction inside of another fraction. Now, when we're talking about rational expressions, a complex rational expression is you got a fraction inside of another fraction with variables in some form. And that's pretty vague, but it really is that vague. Basically, you got a fraction inside of a fraction, you got variables of some kind. Now, simplifying a complex rational expression, and simplifying it means just basically get rid of the fraction inside the fraction. I'm going to give you all the steps here, but there's no problem I've seen in any algebra book that has one this hard. But this is the full steps. Step 1 is to factor all the inner denominators. And we'll see what in the world I mean by that when we look at an example. Now step 2 is to figure out the LCM of all the inner denominators and multiply everything by it. Unless the top or bottom is already in factored form, get rid of parentheses, and combine like terms. And then step 4 is factor the top, factor the bottom, and step 5 is cancel if possible. Okay, let me clear off this page. And I didn't write down which problem this was. I just said it's from page 397. But it's x over x plus 1 minus 1 over x, and then x over x plus 1 plus 1 over x. Notice we have a fraction inside of another fraction. Step 1, factor all the inner denominators. When I say inner denominators, I'm talking about these fractions inside of the other fraction. So that'd be an inner denominator. This one would be. This x plus 1 would be here, and this x plus 1 would be. Well, as you look at those, there are all factored as much as they can be. Step 2, figure out the LCM of all the inner denominators and multiply everything by it. LCM, least common multiple. Well, let's start with our first factor. I'll choose the x. Now I'm looking for the greatest number of single x's in any single inner denominator. When I say single x, it does not include having a plus 1 with it. So there's none here, there's 1 here, there's none here, there's 1 here. So the greatest number of single x's in a single inner denominator is 1. Now I go to my next factor, the x plus 1. And I'm looking for the greatest number of x plus 1's in any single inner denominator. There's 1 here, none here, 1 here, none here. So the greatest number of x plus 1's in a single inner denominator is 1. And this is going to be our LCM. And I say multiply everything by it. So I'm going to multiply it times this first fraction, x over x plus 1. I want to multiply it times the 1 over x. I want to multiply it times the x over x plus 1. And I want to multiply it times the 1 over x. Now books will oftentimes present two different methods for simplifying a complex rational expression. This is the method that works 100% of the time, no matter what the problem looks like. These x plus 1's cancel. These x's cancel here. These x plus 1's cancel here. And these x's cancel here. So we're left with x times x, x squared, minus x plus 1 times 1, which is just x plus 1. Notice I kept the parentheses here, because this minus is going to flip the sign of everything that follows it. Down below here we have x times x, which is x squared, plus x plus 1. So that gives us x squared. Remember, a negative in front of your parentheses flips the sign, everything follows it. So it becomes a minus x minus 1 over x squared plus x plus 1. Step 3. Unless the top and or bottom is already in factored form, get rid of parentheses, combine like terms. That's already done. Step 4. Factor the top, factor the bottom. Well, these don't factor at all. If I tried to do the PSD on these, it wouldn't work. So this is actually our answer. You can't go any further there. And that would be how to simplify a complex rational expression. Now, the next topic is solving rational. I don't have it here. Okay. They have it listed a little bit different in the competencies. They have it over here. I'm going to take it, though, and put it right after here. This is where it logically falls. Okay. Solving rational equations. So solving a rational equation, you don't see why it belongs here after work this problem. First step is to get rid of parentheses. Second step is to get rid of fractions. Now oftentimes on these, to get rid of the fractions, it's going to involve factoring all the denominators, figure out the LCM of all the denominators, C, multiply everything by the LCM, then step 3 will be to solve for x. And that's pretty vague, but it has to be. Could be a linear equation at this point, in which case you'd use your 4-step method we looked at earlier in the course. Or it could be a quadratic, and here you'd use your zero factor property, typically. And then step 4 is to semi-check your answer. You don't have to fully check it, you just have to make sure it doesn't cause any denominator equals 0. And we'll look at that. Let me clear this off. And this is on page 406, number 18. And we got 5 over y plus 3 minus 2 is equal to 7 over y plus 3. Now, what makes this a rational equation is we got a fraction, single fraction here, and specifically we have variables in the denominator. That's what tells us rational equation. Step 1, get rid of parentheses. Don't have any. Step 2, get rid of fractions. Now, the first sub-step says factor all the denominators. Not factoring. Factor all the denominators. Y plus 3, there's nothing to factor. B, figure out the LCM of all the denominators and then multiply everything by it. So these kind of go hand in hand. Now, I'm going to look at my first factor here, the y plus 3. Now, I'm looking for the greatest number of y plus 3's in any single denominator. There's 1 here, there's 1 here. So greatest number of y plus 3's in a single denominator is 1. You notice that's the same question we were asking back on adding and subtracting rational expressions and simplifying complex rational expressions. So this is our LCM. There's no other factor. So I'm going to multiply this times everything. I'll multiply it times the 5 over y plus 3. I'll take it and multiply it times the negative 2. And I'll multiply it times the fraction on the right side. Now when I say multiply by everything, I'm talking about what's separated by pluses, minuses, and equals. But you got to keep single fractions together. So you can't split those apart. That's why they're all looked at as one. When I do that, these y plus 3's cancel, and these y plus 3's cancel. So I got 5 minus 2 times y plus 3 is equal to 7. Negative 2 times y is negative 2y. Negative 2 times 3 is negative 6, equals 7. 5 minus 6 is negative 1, is equal to 7. And we're now at, I say solve for x, but it can be any variable. We're now at step 3, solve for y. And this is a linear equation. Reason why it's a linear equation is we got y to the first power. If we had y to the second power, it'd be a quadratic, in which case we'd use the zero factor property. But this says use a 4-step method. Remember, our first step was get rid of parentheses, don't have any. Second step was get rid of fractions, don't have any. Third step was to get everything with a y on one side, numbers on the other side. So I'll take -1 over, and it becomes a positive 1. And 7 plus 1 is 8. And then our last step of solving a linear equation is to divide both sides by a number in front of your y. So divide both sides by -2. And we get y is equal to -4, maybe. We can't forget step 4 that says semi-check your answer. So we're going to take this -4 and we're going to plug it into our original problem, make sure it doesn't cause any denominator to equal 0. If I put -4 here, -4 plus 3 is -1. That's not 0. -4 plus 3 is again -1. That's not 0. So our answer would actually be -4. Now if I'd come up with a -3, for example, if I put -3 back up here, -3 plus 3 would give me a 0 in the denominator, which means I couldn't use that answer. And if you didn't have any other answers, your answer would be no solution. So again, you don't have to fully check it. You just need to make sure this doesn't cause any denominator to equal 0. And next one's a little bit harder, so let me clear this off. This is page 406, number 34. And I got 9 over x squared plus 7x plus 10 equals 5 over x plus 2 minus 3 over x plus 5. Okay, step 1, get rid of parentheses. Don't have any. Step 2, get rid of fractions. And I say factor all the denominators. Well, this one I can factor as PSD. X plus 2 and x plus 5 I can't do anything with. So this becomes 9 over x plus 2, x plus 5 equals 5 over x plus 2 minus 3 over x plus 5. And that was A. Factor all your denominators. Now B and C, again, kind of go hand in hand. B says figure out the LCM of all the denominators. So I start with my first factor, the x plus 2. I'm looking for the greatest number of x plus 2's in a single denominator. There's one here, none here. So greatest number of x plus 2's in a single denominator is 1. Then I go to my next factor, the x plus 5. And I'm looking for the greatest number of x plus 5's in a single denominator. There's one here, none here, 1 here. So greatest number of x plus 5's is 1. So this would be our LCM. And this is what we're going to multiply everything by. We'll multiply it times our first fraction. We'll multiply it times the first fraction on the right side. And we'll multiply it times this last fraction. Notice I'm putting it after it. I'm doing that just so I don't lose track of this negative right here. Okay, that x plus 2 cancels to that x plus 2. This x plus 5 cancels to that. This x plus 2 and this x plus 2 cancel. And this x plus 5 and this x plus 5 cancel. So we're left with 9 equals 5 times x plus 5 minus 3 times x plus 2. Distributive property, 5 times x is 5x, 5 times 5 is 25. Negative 3 times x is negative 3x, negative 3 times 2 is negative 6. 5x minus 3x is 2x, 25 minus 6 is 19. And I didn't mean to do this, but I think this is one of them will be a no solution. I just picked these out at random. I'm looking for interesting problems. Okay, step 3, solve for x. This is a linear equation. because we got x to the first power. So get rid of parentheses, first step, don't have any. Get rid of fractions, don't have any. Get everything with an x on one side, numbers on the other side. So I'll take 19 over. It becomes a negative 19. 9 minus 19 is negative 10 equals 2x. And last step is to divide both sides by a number in front of your x. Number in front of our x is a 2, so divide both sides by 2. And we get x is equal to negative 5. Maybe. Because remember, step 4 says we have to semi-check our answer. If I take the negative 5, plug it back up here, specifically if I pick this last fraction, I can see right away it causes me problems. Because negative 5 plus 5 would give me a 0 in the denominator, which means my answer is no solution. If it causes just one denominator to equal 0, you don't even need to plug it in the other ones. It's not going to be one of your answers. Now the next topic, and I probably don't got this in the right order again, that was solving rational equations, is solving proportions. So put that over here. Move a couple of these to the next page. There we go. Okay, so solving proportions. And proportions is something you can probably use in many different aspects in life. Probably I'd be shocked if you ever use a rational equation. But if you I give an example in the discussion where I'm talking about how I use it in web design. But if you were looking at that, let's say this is 2 inches, and your 2 inches represents 1 mile. You're looking at a map, for example. And this distance here was, let's say, 1.1 inches. And you're wondering how many miles that's equal to. Well, it's close to half a mile, because this is almost half of this. Well, what we can do is you got your inches. 2 inches is equal to 1 mile. You set up a relation like this, so inches to miles, and then we want to know 1.1 inches, and we're wanting to know how many miles goes down here. Well, if we strip out all the units of measure, we'd have 2 over 1 is equal to 1.1 over, and I put an x in there. So if I cross multiply, we got 2 times x and 1 times 1.1. You can always cross multiply when you got a single fraction equal to single fraction. Now that's the only time you can actually cross multiply. And so that'd give us 2x is equal to 1.1, and then divide both sides by 2. And 510.55, I believe. Not very good with decimals, but that would be how many miles. And it doesn't matter what you're trying to relate, you can set it up in that form. A lot of the word problems, application problems, are centered around this concept here. Now, that's one way of doing proportions. There's another way. Some people like to put like the inches here, and they'll put the inches here. And then 2 inches relates to 1 mile. And then down here, you would put your x miles. So it doesn't matter how you do it. Just this way, I find people mess up the problems more, make more mistakes. This here, you can see what directly relates. 2 inches relates to 1 mile. You can put them in the same fraction. And then 1.1 inches, we're wondering, relates to how many miles. Now that's a setup on them. I used proportions when I worked in the motel, doing the night shift, and also prepared breakfast. When they got the waffle machine, they calculated the formula wrong, and they didn't want to make a full batch. I figured if they wanted to make 3/4 of a batch or half a batch, and they tried to do the algebra, and it was all messed up. I could tell before I even made the first batch because they told me to try it. I think they recognized their formula wasn't right, and I just set up a simple proportion like this to figure out how much flour or how much of the powder or water I should use. Okay, let's take a look at an example out of the book on this. First off, let me point this out. This is not a proportion. Proportion means single fraction equal to single fraction, so you cannot cross multiply on this. You have to use the technique I showed. So let me get that cleared off. And we'll look at number 19. So we got 8 over x minus 5 is equal to 3 over x. Okay. Now since I got a single fraction equal to single fraction, this is where you can cross multiply. So we can take 3 times x minus 5, and we can take 8 times x. And then 3 times x is 3x, 3 times negative 5 is negative 15, 8 times x is 8x. I'm going to take this 3x, move it to the right side, and it becomes a negative 3x. 8x minus 3x gives us 5x, and then I'll divide both sides by 5. And we get x is equal to negative 3. Now, we still have to check it to make sure it doesn't cause the denominator to equal 0. If I put negative 3 up here, negative 3 minus 5 is negative 8. If I put negative 3 here, it's negative 3. Neither one gives us 0 in the denominator, and that's the only thing we're worried about. So that would be our answer. And that would be solving proportions. It looks like I'm missing one here. Simplifying radicals. Now, they have this in one of the sections, but they don't actually list it as one of the items to be covered. But you need to know how to simplify the radicals in order to do a lot of these problems. So we're going to talk about that first. And I made up 3 examples. The first one is a square root of 24. This symbol right here is square root. Well, what we do is we to simplify this, and that's what the instructions are on all these, is simplify. And that's always implied. No matter where you run across a radical in algebra, you should always try to simplify it. Now, if I do the prime factorization, 24 is 2, 4, 8 times 3. Now, you're not very good at coming up with prime factorization. Your primes are 2, 3, 5, 7, and 11. And remember, you can do the tree breakdown. So 24, I start with my first prime, is divisible by 2. 2 times 12. 2's prime size circlet. 12 is 2 times 6. 2's prime size circlet. And 6 is 2 times 3. And 2's prime size circlet and 3's prime size circlet. Now with square roots, we're looking for pairs of something. Here we got a pair of 2's. So a pair of 2's is going to come out in front as a single 2. And then we're left with a 2 times 3 in sides, which would give us 6. I can't bring any of that out because there's not a pair of them. And with square roots, we're looking for pairs of whatever. So that'd be our answer. Now let's look at 16 x to the 11th, y to the 5th inside of a square root. First I'm going to do this the hard way, and then I'll talk about the shortcut. 16 is 2, 4, 8, 16. X to the 11th, we got 11 x's. 3, 4, 5, 6, 7, 8, 9, 10, 11. 3, 6, 9, 11. Okay. And y to the 5th, we got 5 y's. You can obviously see a problem right here. If this had been 110, I wouldn't want to write out 110 x's. But we'll get to that in a minute. Now we're simplifying a square root, so we're still looking for a pair of somethings. Here's a pair of 2's, so they're going to come out in front. Here's another pair of 2's, so they're going to come out in front. Here's a pair of x's, they're going to come out as a single x. Here's another pair of x's, they'll come out as a single x. Another pair of x's, single x. Another pair of x's, single x. Another pair of x's, single x. Here's just a single x. I can't bring it out because I need pairs of something. Here's a pair of y's. They're going to come out as a single y. And here's another pair of y's. They'll come out as a single y. Okay, so I'm going to have a 2, 2 from here. And let's see how many x's we got. 1, 2, 3, 4, 5 x's. 1, 2, 3, 4, 5. And we got 2 y's. Remember, the pair comes out as a single one of them. And we're left with an x and a y inside. Well, when they come out with multiplication in between them. So 2 times 2 is 4. And we got 5 x's, so that's x to the 5th. And we got 2 y's, so that's y squared. And that would be our answer. Now let me grab a drink, and then we'll take a look at the shortcut. Because obviously that was kind of tedious. Okay, so I got square root of 16 x to the 11th, y to the 5th. We don't actually write out our variables like that. But the number I can. I could also write 4 times 4 if I see that. It doesn't have to be the complete prime factorization. Because remember, all we're looking for is a pair of somethings. Well, first off, this pair of 4's will come out front as a single 4. Now, let's take a look at the x's. What we can do is we're going to take the power, the 11, and we're going to divide it by our index. So this is our power, and this is our index. Now if you're wondering, well, where do you get the index at? Index is whatever number is in this little slot right here. And if there is no number in that slot, then it's by default 2. Square root, square, 2. So that's where that 2 comes from. Now this is old style division. 11 divided by 2 is 5 with a remainder of 1. Remember the R, so you do it that way. Now this 5 here tells us how many are going to come out. So that means there's 5 x's going to come out. And this tells us how many x's is going to stay in. So that says we're going to bring out 5 x's. And we're going to have 1 x stay inside. We can use the same technique to figure out how many y's are going to come out. We have a 5 here. So you take your power, divide by your index. And again, this is old style division. So 5 divided by 2 is 2 with a remainder of 1. This tells us how many are going to come out. And this tells us how many are going to stay in. So we're going to have 2 y's come out. And we'll have 1 y stay in. Which we see then is 4x to the 5th, y squared, the square root of xy, which gives us the same answer without writing out all those x's and y's. Now, we're going to see another example of this technique, but I'll choose one with a cube root. But much easier way to do it. Most of the time you'll get to the point where you do that in your head and figuring out how many to bring out. Let's take a look at another example. And I made up a cube root of 8, x to the 16th, y to the 9th. Now number-wise, you treat it just like before. 8 is 2 times 2 times 2. Now to simplify this one, the number in this slot right here, that's our index. Our index is now equal to 3. Which means instead of looking for a pair of somethings, we're looking for 3, a set of 3 of something. Well, here I got 3 2's. So those 3 2's going to come out in front as a single 2. Now let's look at our x's. We take our power, divide by our index. So power divide by our index. Again, the power is whatever power it has right here, and the index is whatever numbers in this slot. So 16 divided by 3 is 5 with a remainder of 1. So that means I'm going to have 5 come out, and I'll have 1 stay in. So we'll have 5 x's come out, and we'll have 1 x stay inside. Now for our y's. Our power is 9, so we're going to have 9 divided by our index. That gives us 3 with a remainder of 0. So this tells me how many I'm going to have come out, and this tells me how many I'm going to have stay in. So I have 3 y's come out, and I have no y stay in. So our answer would just be 2x to the 5th, y to the 3rd, the cube root of x. That first power I can drop. Now that's simplifying radicals. That's that topic right there. And then all of a sudden I go from radicals and I start talking about rational exponents. And we're going to see why here in a minute. First, we're just going to look at some properties dealing with rational exponents, and then we'll see why are we mixing the two together. So let me clear that off. This is on page 445, number 20. We got a to the 1/3 times a to the 5/3. Now before we looked at problems that look like this. X squared times x to the 3rd. And what we did is we, if these are both the same, both x to a power, then you add the exponents. 2 plus 3 would give us x to the 5th. Well, now they're taking what we learned before, and they're mixing in fractional powers, rational exponents. It's still the same idea. These are both a to a power. So I'm going to add the exponents. So I got 1/3 plus 5/3 gives us a to the 6/3. And 6 divided by 3 gives us a squared. And that would be our answer. Let's take a look at number 27. We've got a to the 1/2 over a to the 3/2. Well, let's refresh our memory. When we had problems that look like this, where we had x squared over x to the fifth, well, we subtracted the smaller exponent from the larger one. So we took 5 minus 2, would give us 3. And we had x to this power where the larger exponent was, which was on the bottom. And then we put a 1 up here in the other location. So again, if you got x to a power over x to a power, subtract the smaller exponent from the larger one, and then you have x to this power where your larger exponent was located. Well, this is no different. We have a to a power over a to a power, so we're going to subtract the smaller exponent from the larger one. So 3 halves minus 1 half gives us 2 halves, which gives us 1. So we're going to have a to the first power where our larger exponent was, which was on the bottom. And then I'll put a placeholder of 1 here, which then simply gives us 1 over a. Let's see, number 30. We got x to the negative 3/5 over x to the 1/5. And if you remember from before, if we had like x to the negative 2 over x to the 5th power, remember how we handled negative exponents. We never liked negative exponents, so we always move it opposite of where it's at in a fraction. So I take this x to the negative 2, move it down below, and it would become the x to the 5th remains where it was, but the x to the negative 2 becomes x to the positive 2. And then you got x to a power times x to a power, you add the exponents, and 5 plus 2 gives you 7. So you got 1 over x to the 7th. Again, the fact that these are fractions does not change anything. It's the exact same principle. There's really not a whole lot new in this part right here. They're just introducing these same ideas that we saw before apply to fractional powers. So I'm going to take this x to the negative 3/5 and move it down below. And so this x to the 1/5 remains where it was. And this x to the negative 3/5 becomes x to the positive 3/5. Well, now we have x to a power times x to a power, so you're going to add the exponents. 1/5 plus 3/5 gives us 4/5. And that would be our answer. Now let me clear that off. And we'll look at some more to refresh our memory. This is number 42. We got b to the 2/3 and b to the 1/6. Well, before, and I don't remember if we had any exactly like this, but order of operations tells us what to do. And order of operations told us to do what's inside the parentheses first. So we got x to a power times x to a power, so you add the exponents. 2 plus 5 is 7. Now remember at this point, when you're raising one exponent to another exponent, you multiply the exponents together. So it takes 7 times 3, which would give us x to the 21st. Well, we'll do the same thing over here. We got b to a power times b to a power, so we're going to add the exponents. So I got 2/3 plus 1/6. Now I need to get a common denominator to add these together, which would be 6. So this becomes b to the 4/6 plus 1/6. On the first fraction, I multiply the bottom part by 2, so multiply the top part by 2. That's why it becomes 4/6. Which then gives us b, 4/6 plus 1/6 is 5/6. So So then I'm going to raise this exponent to another exponent. So I'll multiply them together. So I'll take 5, 6 times 6. No 6 is going to cancel, and we get b to the 5th. And that'd be our answer. So again, same idea as this, we're just not dealing with fractions. Number 57. We got x to the 1/4, x to the negative 1/2, and then we got x to the 2/3. And I might have enough room. First thing I notice is I have a negative exponent. Never want negative exponents. So I'll take this down below. So we're going to have x to the 1/4 over x to the 2/3 times x to the 1/2. Now I notice that all three of these fractional powers have different denominators. And I know eventually I'm going to somehow want to merge them all together, whether I'm adding or subtracting. So I'm going to go ahead and get them all to the same denominator. My LCM of 4, 3, and 2, my common denominator, would be 12. So this becomes, multiply the bottom part by 3, multiply the top part by 3. So that's x to the 3/12. Here I multiply the bottom part by 4, so multiply the top part by 4. So that's x to the 8/12. Here I multiply the bottom part by 6, so I multiply the top part by 6, and that gives us x to the 6/12. Okay. Now the top remains as is. Here we got x to the 8/12 times x to the 6/12, so you're going to add the exponents. So that gives us 8 plus 6 is 14/12. Now we have x to a power over x to a power. Remember, we're going to subtract the smaller exponent from the larger one. So 14/12 minus 3/12 gives us 11/12. So we're going to have x to 11/12 where our larger exponent was, which is on the bottom. And then we'll put a placeholder of 1 in the other position. And that would be our answer. Like that should have came out nicer, but I'm checking through, I don't see anything wrong with my math. Been nice if that had been 12 over 12, then it would have just been x. Now let's clear this off and look at another example. Now it may seem like these are random examples I'm just pulling out of the air. That's about right. What you're going to find is that each one of these is kind of different. But they all go back to the basic properties of exponents we've seen before. This one, number 74, we got x to the 4/3, if I'm reading my writing right, times x to the 2/3 plus x to the negative 1/3. Just as long as you're using some kind of property, then it doesn't matter what order you go in. Remember when we looked at problems look like this? X times x plus 3. We took this on x, multiplied times the x here, and times the 3. And that gave us x squared plus 3x. X to the first power times x to the first power, we again added the exponents. No different here. We can take the x to the 4/3 and multiply it times both items here, distributive property. So that's going to give us x to the 4/3 times x to the 2/3. Let me write it out. And I'll have x to the 4/3 times x to the negative 1/3. Remember, if you have x to a power times x to a power, you add the exponents. 4/3 plus 2/3 gives us 6/3. And 4/3 plus negative 1/3 gives us 3/3. 6 divided by 3 is 2, so we got x squared plus 3 divided by 3 is 1. So that's x to the first or just x. So that'd give us our answer. Notice I did not focus on getting rid of the negative exponent here. I instead opted to use the distributive property. Again, it doesn't matter the order, just as long as you do a valid property, a valid math operation, then you'll get to the same answer. Now, that's simplifying expressions with rational exponents. Now, if we look at converting between exponential and radical expressions, I said we would make the connection between these fractional powers and our radicals. If we have the square root of x, for example, if I were to put a power on here, this is like x the first. You can always put a first power here. And if I were to put the index in here, that would be 2. I can rewrite this in fractional power form. This would be x to the 1/2 power. Now how that works is whatever power is right here goes up on top, and whatever number's in this slot here, your index, is what goes down below. So actually, when we're working with fractional powers, we're working with radicals. Now consider another example. Cube root of, I don't know, x to the 5th. I could, of course, simplify that, but if I'm just going to rewrite it into this form, this would be x to the 5/3 power. Again, whatever power is right here goes up on top, and whatever your index is what goes down in the denominator. Now you can have a little bit more than just like a single item down there. You could have like 3xy inside here. You might be saying, well, how do you handle it then? Well, imagine that if I had parentheses here, what power this would be to? Well, this would be the first power. In my index, there's blank here, square root, so that means it's a 2. So then that becomes 3xy inside of parentheses to the 1/2 power. Now let's look at going the other direction. If we had x to the 2/3, for example. Well, this would be the cube root of x squared. Going in the other direction, whatever number is in your denominator, that goes in the slot, that's your index. And whatever number's up on top is your power, and it can go right there. So that's going back and forth between the forms. Why would you want to do this? Sometimes it's easier to work with fractional powers than it is to work with radicals. You get a fractional power, you got a lot more flexibility. You can get common denominators, you can do all the different things we know with fractions. Okay, that's converting between exponential and radical expressions. Now let's take a look at adding and subtracting radical expressions. So let me clear off this page. And this is off of page 456, number 36. And we got 3 square root of y plus 12 square root of y. Now we talked about combining like terms earlier in the course, and it probably actually should be something more like combining like items, whatever that means. If this item here is the same as this item, excluding the numbers in front of them, no matter what it looks like, then you add or subtract the numbers that are in front of them. Since these are both square root of y's, 3 plus 12 would give us 15 square root of y. And that would be our answer. Like items. It doesn't matter what you're working with. If I had smiley faces, 3 smiley faces plus 12 smiley faces, since these are both the same, that would give us 15 smiley faces. If you go on and take trig, if you have 3 sine x plus 12 sine x, Maybe I have no clue what sine x is. Doesn't matter. If this is the same as this, they're like items, then you add or subtract the numbers in front of them. 3 plus 12 is 15 sine x. So again, it's the concept of combining together like items. Of course, there has to be some kind of twist to it, of course. So number 44 shows one of those. If we have 5y square root of 8y plus 2 square root of 50 y to the third, you can obviously see these are not alike. Square root of 8y and square root of 50 y to the third. But I can simplify these. Remember, I mentioned that earlier. I said you should simplify radicals before you do anything. 8 is 2 times 2 times 2 with a y. 50 is 2 times 5 times 5. Now y to the third, since there's just a few of them, I'll go ahead and put 3 y's. I won't use my shortcut here. Now remember, square roots, we're looking for a pair of somethings. Here's a pair of 2's, so they're going to come out in front as a single 2. Here's a pair of 5's, they're going to come out in front as a single 5. And here's a pair of y's, they'll come out in front as a single y. So we have 5y times 2, then we're left with a 2y inside. Over here, the pair of 5's comes out as a single 5, the pair of y's comes out as a single y. And we're left with a 2 and a y inside. Five times 2 is 10, so we got 10y square root of 2y plus 2 times 5 is 10y square root of 2y. Like items, excluding the number in front of them, but the number in front of them is actually the same too, but ignore that fact. These would both be alike because they both have a y square root of 2y, which means we'd add or subtract the numbers that are in front. Well, 10 plus 10 is 20, and then y square root of 2y. And that would be our answer. So again, if you can get them looking exactly alike, except for possibly the numbers in front of them, then you just add or subtract the numbers in front, and then whatever follows just stays the same. Now that was adding and subtracting radical expressions. It doesn't matter whether you got addition or subtraction, the same principle holds true. Now let's take a look at multiplying radical expressions. Let me clear this off. Fairly simple idea. This is number 76 on page 457. We got the cube root of 4a squared b to the third times the cube root of 8a b to the fifth. Now the book will give you the property on this. I'm not going to write down the property. The property will make it look pretty complex, but it's much simpler than that. If you're multiplying two radicals together and they have the same index, and that's key, they both have to have the same index, then what you do is you just put them together inside of a single radical with multiplication. So I got 4 times 8, I got a squared times a, and I got b to the third times b to the fifth. So again, with multiplication, assuming your index is the same, you just multiply what's underneath the radicals and put them underneath a single radical. Now I say multiply them together, but you don't actually want to multiply them together, because your hope is that something will simplify. So 4 is 2 times 2, and 8 is 3 2's. A squared is 2a's, and then a single a. I should probably use my shortcut here, but this is still not too many. 3 b's, 5 b's. Now our index is 3, which means we're looking for a set of 3 of something. And let me do this in a different color, I guess. Here's 3 2's, so they're going to come out in front as a single 2. Here's 3 A's, so they're going to come out in front as a single A. Here's 3 B's, so they'll come out in front as a single B. And here's 3 B's, so they'll come out in front as a single B. So we got this set of 3 coming out as a single 2. This set of 3 A's comes out as a single A. This set of B's comes out as a single B. And this set of B's comes out as a single B. And let's see what's left inside. 2 times 2 is 4. And 2 B's. So B squared. So then we got 2A B squared and cube root of 4B squared. And now be our answer. Now you won't have any problems that involve different indexes. Like I looked through and I didn't see any, maybe famous last words, but I didn't see any where one of them had like an index of 3 and the other one had an index of 5. Those get a lot trickier. You have to put them in fractional power form, rational exponents, and get a common denominator, and then put them back in the radical form. Let's look at another multiplication. Number 94. And we got square root of y minus 2 times square root of y plus 2. If you remember, like x minus 1 times x plus 3, we multiply these together, FOIL it, if you learned that technique. X times x is x squared. X times 3 is 3x. Negative 1 times x is negative 1x. Negative 1 times 3 is negative 3. And then we'd combine together like terms. Now this is no different. We're still going to FOIL it. So I'll multiply the square root of y. Let me show you the lines, what I'm going to multiply together. This square root of y times this square root of y, and times a 2. And then I'll take the negative 2 and multiply it times this square root of y and times this positive 2. So square root of y times square root of y, that's the first. And then square root of y times 2, that's the outer. Negative 2 times square root of y, that's the inner. And negative 2 times 2, that's the last. Or I'm just following these lines to see what to multiply together. Now I already mentioned, if we're going to multiply radicals, all you do is multiply and put them underneath a single radical. So square root of y times square root of y gives us square root of y times y. Square root of y times 2 is 2 square root of y minus 2 square root of y minus 2 times 2 is 4. Now remember, with square roots, we're looking for a pair of somethings. Here's a pair of y's, so they're going to come out in front as a single y. Now these are both square root of y's, so I can add or subtract the numbers in front. 2 minus 2 is 0, so those basically cancel each other away. So the minus 4 carries down, and this would be our answer. Those are actually called conjugates too. And if you remember that, all you have to do with conjugates is multiply your first parts together and your last parts. Conjugate means the first part's the same, square root of y and square root of y. Last part's the same, 2 and 2, but the sign in the middle is different. When you got conjugates, all you have to do is multiply your first parts and your last parts, because the middle parts will always drop away. Now that's multiplying. Let's talk about dividing radical expressions. And let me clear this off. And dividing. We got some notes on division. So dividing, also known as fractions, and radicals. We got two items we can't have. No fractions inside of a radical. Second item is no radicals in a denominator. So those are the two items we can't have. So let's take a look at how to handle those. The first one, this is still off of page 457 or around that area. Number 110. We got square root of 60 y to the fourth over square root of 12y. Now the problem here is that we got a radical in our denominator. That's our main issue. Besides, we could simplify. We got a property. And this property is not too confusing, so I'll put it down. And the property says if you have a radical, whatever your index might be, usually they put some kind of letter here, but I'll leave it off just for simplicity's sake. If you got a radical of a fraction, you can split this up. You can put a radical around the top, and you can put a radical around the bottom. Now you can go either direction. If you have the fraction inside here, you can go this way. Or if you have a radical over a radical, you can go in this direction. Well, in this one, I'm going to put them together into a single radical. Now the reason why I'm doing that is because it looks like when I did that, I could simplify these then. Now 60 and 12 are both divisible by 12. 60 divided by 12 is 5. 12 divided by 12 is 1. This one we have y to a power over y to a power. Remember, if you have that, you subtract the smaller exponent from the larger one. 4 minus 1 is 3. And we'll have y to the third where the larger exponent was, which was on top. Now all of a sudden we got a 1 down here, so this just simply becomes a square root of 5y to the third. Now that we can simplify some though, because y to the third is 3y's. And remember, with square roots, we're looking for a pair of somethings. So this pair of y is going to come out as a single y. So we got y square root of 5y. And that's our answer. Now let's take a look at another example. Number 113. We got 1 over the square root of 5. Well, we got a problem here. We said no radicals in the denominator. We have a square root down here. Can't have that. Now when you have a square root down below, how we're going to get rid of it is we're going to multiply the top and bottom by that square root. And we're going to see why that actually works. 1 times square root of 5 is square root of 5. And square root of 5 times square root of 5 is square root of 5 times 5. Remember, when you're multiplying two radicals together, you multiply what's underneath the radicals, put them underneath a single radical. But this is specifically a square root, which means we're looking for a pair of somethings. Here's a pair of 5s, so they're going to come out in front as a single 5. So we have square root of 5 over 5. And notice my radical disappears. Since I took everything out of it, the radical's gone. Now what made it disappear is that our index was 2 and we had a pair of 5s. That's what caused it to disappear. Now you might say, well, that doesn't look simpler, it looks harder. Well, there's no fractions inside of a radical, so that's good. And there's no radicals in the denominator, so that's good. So division, we don't actually divide. We just want to make sure those two criteria are taken care of. Okay, let's look at 119. We got square root of x over 5. Well, the problem here is that we can't have a fraction inside of a radical. But we said in our property we could split this up. We could put a square root on the top and square root on the bottom. And you might be saying, well, we're just trading one problem for another problem. Remember what we said, we can't have any radicals in the denominator. But we looked in this previous problem, we looked at how to get rid of that radical. And we'll do the same thing here. To get rid of that square root of 5, we'll multiply the top and bottom by the square root of 5. So then, square root of x times square root of 5 is square root of x times 5. And square root of 5 times square root of 5 is square root of 5 times 5. Now, square roots, we're looking for a pair of somethings. So here's a pair of 5s, so they're going to come out in front as a single 5. So we've got square root of 5x over 5. No fractions inside of a radical, no radicals in denominator. So that meets our two criteria. Now let me clear off that page. Actually got a couple more of this type I want to show. Page 124, or page 1, number 124, same page. We have 5 over the cube root of 3y. This one's different. Instead of being a square root, it's a cube root, which means I need 3 of whatever. Now here I already have 1 3 here, which means I need 2 more 3's. I already have 1 y, which means I need 2 more y's, because the number of y's has to match your index. Now whatever we multiply by the denominator, we have to multiply by the numerator, so I'll multiply the top part by that also. Okay, so up on top, that's going to give us 5, the cube root of 3 times 3, y times y. Down below, we've got this radical times this radical. So we'll put the numbers together. We got 1 3 here and 2 3's here, so we got 3 of them. We got 1 y here and 2 y's here, so we got 3 y's. Now our index is 3, so we're looking for a set of 3 of something. Nothing up on top, but on the bottom we got 3 3's, so they come out as a single 3. And we got 3 y's, so they'll come out as a single y. So if we have 3 times 3 is 9, y times y is y squared, and down below we have 3 and a y. And that'd be our answer. Now let me make up an example just to really drive that home. If I have the 7th root of x squared, our index is 7, which means we need 7 of whatever. I already have 2 x's, so I would need 5 more x's. And wherever you multiply by the denominator, you have to multiply by the numerator. So that's going to give us a 7th root of x to the 5th over, we got x squared times x to the 5th, which if I were to write all those out, that's 2 x's, that's 5 x's, I got 7 x's. So that's going to end up giving us just a single x down below. So again, the index will drive how many of whatever you need. How many 3's, how many 2's, how many x's, how many y's. Let me clear that off. And next thing we're going to take a look at is solving radical equations. This one does have a step-by-step, so we'll go back to a little bit of step-by-step. So solving a radical equation, our first step is to get a radical by itself on one side, but do not create a fraction. Step 2 is to raise both sides, so I can spell, both sides to a power equal to the index. Step 3, if you have more radicals, go back to step 1. Step 4 is solve for x. And that's pretty vague, It'll either be a linear equation or quadratic equation, but it actually doesn't have to be. It could be anything at that point. And then step 5 is to check your answers. This process gives you the correct answers, but sometimes it gives you false answers, so you have to check it. And you have to check it fully, not like partially like we looked at with rational equations. And I got 3 examples I'm going to show here. There's some harder ones than what I'm going to show, but when I was scouting through looking what material covered, these look like the types would be the best examples. Okay, radical equation. Radical equation, you got an equation, you got a radical. First step, get a radical by itself one side. Now when I say by itself, we don't want anything in front of it, we don't want anything after it, we just want the radical by itself on one side of the equals. Well, that's done. Step 2, raise both sides to a power equal to the index. Remember, the index is whatever number's in this little slot right here. And if there is no number, it's by default 2. So here we'll square both sides. Now what you'll find is when your index matches the power you're raising it to, they cancel each other away. So that gives us 3x minus 2, and 5 squared is 25. Now step 3 says if you have more radicals, go back to step number 1. We don't have any more. So go down to step 4. Solve for x. This is a linear equation, so get rid of parentheses, don't have any, get rid of fractions, don't have any. Get everything with x on one side, numbers on the other side. So I'll take negative 2 over, and it becomes a positive 2. 25 plus 2 is 27. And then last step is divide both sides by 3, the number in front of our x. And we get x is equal to 9 maybe. Because remember, step 5 means you have to check your answer. So I'm going to plug that x equals 9 back in for x. So I got 3 times 9 minus 2. And we're wondering if that's equal to 5. 3 times 9 is 27, minus 2 is 25. And square root of 25 is 5. So we get 5 is equal to 5, and it checks. So this would be our answer. Let's take a look at number 24. We've got the cube root of 3 minus 2x equals negative 2. Step 1, get a radical by itself one side. This is by itself. There's nothing in front of it. There's nothing after it. We just got the cube root by itself on this side. Step 2, raise both sides to a power equal to the index. Remember, your index is whatever number is in this slot, which in this problem is 3. So I'll take both sides to the third power. Now when your index matches the power, they cancel each other away. So you got 3 minus 2x. And negative 2 to the third power, negative 2 times negative 2 is 4, times another negative 2 is negative 8. Step 3, if more radicals, go back to step number 1. We don't have any more. Step 4, solve for x. Well, this one I'm going to take the, I'll take 3, move it over. So we'll get negative 2x is equal to negative 8 minus 3. Negative 2x is equal to negative 11. And divide both sides by negative 2. And we get x is equal to 11 halves. Maybe. Remember, step 5, we have to check it. So if we plug that back in, we're going to have 3 minus 2 times 11 halves. And we're wondering if that's equal to negative 2. Those 2's would cancel. I got 3 minus 11. We're wondering if that's equal to negative 2. 3 minus 11 is negative 8. We're wondering if that's equal to negative 2. Cube root. Remember, we're looking for a set of 3 of something. Well, negative 8 is negative 2 times negative 2 times negative 2. Now, I was pretty vague about that. I said this indicated we need 3 of something. It doesn't matter what it is. Here we got 3 negative 2's. There are a little bit of restrictions if you got an index that's even. But that comes out as negative 2, and we get negative 2 is equal to negative 2, which checks. So that'd be our answer. Okay, let's look at one more of those. And this was a specific type that you needed to know, where you have 2 radicals. So let's see how to handle that. Step 1 says get a radical by itself on one side. Well, this one's by itself. Nothing in front of it, nothing after it. Now notice I was very specific. I said get a radical by itself. So step 2. Raise both sides to a power equal to the index. Well, these are square roots again, so I'll square both sides. Now over here, our index matches the power, so they cancel each other away. So we've got x plus 1. Over on this side, though, we have to rewrite this as 2 minus square root of x times 2 minus square root of x. The reason I can't just square the 2 and square the square root of x is because of the minus in there. The minus screws it up. Now we're going to FOIL those. So we'll take 2 times 2. We'll take 2 times negative square root of x. We'll take negative square root of x times 2. And we'll take negative square root of x times negative square root of x. That's your FOIL. First, outer, inner, last. 2 times 2 is 4. 2 times negative square root of x is negative 2 square root of x. Negative square root of x times 2 is negative 2 square root of x. Negative times negative is positive, and square root of x times square root of x gives us square root of x times x. I said earlier we want to look at combining like items. Here's a square root of x and here's square root of x, so we can work with those. 4 carries down. Negative 2 and negative 2 gives us negative 4 square root of x. And notice here we got a pair of x's. So this pair of x's is going to come out in front as a single x. Now at this point, you notice that our radical is still there. So step 3 says if you have more radicals, go back to step number 1. We're going to start over. Step 1, get a radical by itself. Okay, I'm going to take this negative 4 square root of x. I'll take it to the left side. Now I'll take both of these over to the right side. You take anything across your equals, your sign changes. So the negative 4 square root of x becomes a positive 4 square root of x. And this x and this plus 4 are still here. I take this x over, it becomes a negative x. I take this 1 over, it becomes a negative 1. Now x minus x drops away. 4 minus 1 is 3. Now the radical's not quite by itself, but I say do not create a fraction. To get it by itself, I'd have to divide both sides by 4. And these are hard enough. Don't create a fraction if you don't have to. Step 2, raise both sides to a power equal to the index. So we'll square both sides again. So we've got 4 square root of x squared is equal to 3 squared. Now over on this side, since everything's multiplication, that means I can take the 4 to the second power and the square root of x to the second power. So that gives us 4 squared and square root of x squared. And 3 squared is 9. So that gives us 16. And when the index matches power, they cancel each other. So that gives us x equals 9. and divide both sides by 16, we get x is equal to 9/16, maybe. Remember, we have to check that up here. So if I check it, I'm going to have the square root of 9/16 plus 1. And we're wondering if that's equal to 2 minus square root of 9/16. This is a mixed number. 1 times 16 is 16 plus 9 is 25. So we've got square root of 25/16. 2 minus 9/16 is 9 is 3 times 3, and 16 is 4 times 4. So basically we've got 3/4 times 3/4. And this is 5 times 5, and that's 4 times 4. So that becomes 5/4 is equal to, or possibly equal to, 2 minus 3/4. Now 2 minus 3/4, that's a mixed number form. 2 times 4 is 8, plus negative 3 is 5, so we end up with 5/4. So it checks. So that's our answer. They're not very nice when there's two radicals usually. Now, there's one other topic. I wrote down some problems, but I don't think I have it on here. It's dealing with complex numbers. And the material doesn't go into it in a whole lot of depth, but I just need to mention some items. Whenever you have a square root of -1, that's always going to give you an I. So this is on page 42, number 10. And we got square root of -64. So we want to simplify that. Well, -64 is -1 times 8 times 8. Remember, we're looking for a pair of somethings. Here's a pair of 8, so that's going to come out in front. And we also have a -1. That'll come out as an I. So this gives you 8I. I'm not going to go into what I represents. The book will talk more about it. Electrical engineering is where you see a lot of it. Now let's take a look at a problem, number 28, where we got square root of 25b minus the square root of -48 b squared. And I know I'm going kind of long tonight, but after this one I only got 2 more examples, and I need to just talk real quickly about the Pythagorean theorem. Always simplify your radicals before you do anything else. 25 is 5 times 5. And over here, -48, that's -1 times 2, 4, 8, 16 times 3. And b squared is 2 b's. 2, 4, 8, 16, 48. Now remember, we're looking for a pair of somethings. Here's a pair of 5s, so that's going to come out in front as a single 5. This -1 will come out as an I. I'll have a pair of 2s comes out as a single 2. Another pair of 2s comes out as a single 2, and a pair of b's comes out as a single b. So we're going to have 5 square root of b minus 2 times 2 times b, and then I. The I comes from the -1, and we're left with a 3 inside. So we're going to have 5 square root of b minus 4b I square root of 3. A lot of times you'll see them put the I after the square root. And to be honest, I don't remember from the book what they do in this. But again, you could write that as 5 square root of b minus 4b square root of 3i. Now obviously you can't combine those together, because this is not the same as this. So that's our answer right there. Now let's take a look at one with, actually I guess I just got one more example. Let's take a look at one with already I's in the problem. This is like number 39. We have 6 minus 9i plus 4 plus 2i. Well, those parentheses aren't doing anything, so I can drop them. So I got 6 minus 9i plus 4 plus 2i. Combining like items. Well, we combine numbers. 6 plus 4 is 10. Now notice here, these both have an I. And I said earlier, I said that you can combine like items just as long as they're exactly the same. Then you add or subtract the numbers that are in front. Negative 9 plus 2 gives us negative 7i. And that would be our answer. Now the last thing. They don't specifically have this on the topics, but I noticed it's mixed in and they expect you to know the Pythagorean theorem. It's a fairly simple idea. Assuming I can spell Pythagorean. That's probably close. What the Pythagorean theorem says is if you got a right triangle, which means you got a sharp corner here, 90 degrees, and let's say this side is a distance of A, and this side here is a distance of B, and this side here is a distance of C. This side opposite of the sharp corner is called the hypotenuse. But anyway, your Pythagorean theorem says that you're going to have A squared plus B squared is equal to C squared. Now how to help you figure out how to set up a problem, let me give you an example. One summer I coached on baseball. They asked if somebody would be willing to coach, because nobody was willing to step forward. Now I said, well, I don't know anything about coaching or baseball, but I said I'll do it so the kids can play, because they're going to have to cancel otherwise. It was a poor league, and we had to put our bases down. And I forget exactly how many feet you went out. I think it was 60 feet to first base, and then the second base was supposed to be 60 feet. That was supposed to be 60 feet, and then this was supposed to be 60 feet. But I didn't. I had a hard time getting this right. As you can tell from my picture here, that's more than 60 feet. Well, they penalized you. So what I did instead is I had I came out, dropped first base. I was, I think, 60 or 75, I forget. I came and dropped second base. That was 60. Then this forms a right triangle. Here's my sharp corner, which means that this distance here would be my C. So from the Pythagorean theorem, I would say C squared is equal to 60 squared plus 60 squared. 60 squared was that 3600 plus 3600, which gives us 7200. And then I drop the second power and I put the square root around this, and we get this. Now if they had given me a rule book, then probably it would tell what that distance is from second base to home. I didn't have that though. And I knew it'd be easier for me to just do the algebra on this than try to Google it and try to find out what that distance is. But this then gave me whatever that square root of 7200 gives you when you plug it in your calculator. And that allowed me, I had one of the boys help me measure this distance, and I did the adjustment right at this point. And once I made the adjustment here, then when I dropped third base and went here, then the distances were okay, and we didn't get penalized. So again, you have to look at whatever problem they give you and see if you can think of a right triangle being there. And then plug in appropriate values and solve for it. Now that's the last topic. Is there any questions on any of that?
No.
Okay, I'll go ahead and stop the recording, and if you have any problems on the quizzes or the unit exam, then I'll go ahead and answer that.